transmission of uniform motion without slip is required, gears are used. The gear drives ensure positive transmission of motion. When two cylinders are in contact, the point of contact is called pitch point. Similarly, when two gears are in mesh, the teeth make contact at pitch point. The imaginary circle passing through the pitch point is the pitch circle. This is the reference circle of the gear. Gears are normally of different kinds. The simpler and more familiar form of gear is spur gear. It is used to transmit motion exclusively between shafts parallel to each other. Spur gear is a cylindrical blank having parallel grooves on its periphery. The radial distance between pitch circle and outside circle is called the addendum of the tooth. The radial distance between pitch circle and the root circle is dedendum of the tooth. When two teeth are in mesh, addendum of one tooth fits into dedendum of the meshing tooth, leaving a small clearance. Thus, the working depth of mating gears is twice the addendum. Since the dedendum is greater than addendum, the total depth of tooth is the sum of addendum and dedendum. The spur gear is so designed that before one tooth gets out of mesh, another tooth comes in mesh to take the load. This tooth mesh cycle provides continuous engagement, causing the motion smooth without jerk and noise. When mesh teeth are in action, the contact and pressure take place at pitch point P. The line of action takes place at an angle to AB. This angle is called pressure angle. It is normally standardized as 20 degrees for all practical purposes. The pressure angle decides the minimum number of teeth necessary for continuous engagement to have good contact with full tooth depth. The mating gear action is one of sliding and rolling. The sliding takes place along the tooth surface before and after the pitch point. But at the pitch point, there is zero sliding. Here, rolling takes place. Thus, at the pitch point, true contact is obtained between two mating gears. For an effective sliding and rolling, the tooth form plays an important role. Experience over the years has proved that the involute curve form has the greatest advantage among various forms of gear tooth shapes. The base circle is drawn tangential to the line of action CD. The tooth shape between the base circle and the outer circle EF takes the form of an involute. The portion between the base circle and the root circle FG is fillet, which increases the strength of the tooth. The involute curve of tooth varies corresponding with the diameter of base circle of gear. Mesh cycle causes continuous engagement. Pressure angle determines the minimum number of teeth. Involute curve facilitates smooth sliding and rolling. Spur gears are produced by different methods. The primitive method is the sand casting process, which produces coarse quality gears. The cast gears are for slow speed applications and where high accuracy is not a prime factor. Gears are also produced from plastic materials by injection molding. This method is employed where quietness, insulating properties, and moderate strength for light services are needed. To transmit high torque at greater speed with accuracy, gears made by metal removing process is preferred. In form milling process, the cutter has a profile similar to the form of the tooth space. The tooth space is a copy of the cutter. A wide range of cutters is required for gears of different number of teeth with different base circles. Hence, in practice, each module range includes a set of 8 standard cutters, producing an average result which is a fair approximation to the ideal. The working gear drawing provides all the necessary data for gear forming on a milling machine. The cutter selected for the given condition is number 4 of 2 mm module, which will produce the required involute tooth form for 28 teeth. The selected cutter is mounted on the arbor of the milling machine. In order to fit squarely on the fixture, the blank dia, the bore, and the working faces are machined true to each other. The job is moved so that the cutter is centered to the marked line, and thus centering of cutter is obtained. First zero setting is made using a thin paper to judge the exact contact point of the cutter on the job. This 0 point is the reference for setting the depth of cut. According to the design calculation, the tooth depth is set for a rough cut on the vertical feed called a knee. Then the periphery of the blank is divided into the required number of teeth. During cutting operation, cutting oil lubricant is used in order to keep the cutting edges of the cutter cool. On the completion of one rough cut, approximately 3/4 of the total depth, the job is indexed for the next tooth. The operation is repeated for all the teeth. Cutting of spur gear on a standard milling machine is carried out where production of a fewer number of gears are required. After cutting all the teeth, the depth is set for finish cut, and the same process is repeated. When mass production of spur gears with high accuracy and high speed applications are required, gear generation is employed. In case of large gears, an initial rough cut is made before taking them for gear generation in order to quicken the process. Gear shaping using rack cutter is one of the gear generation methods. The rack cutter reciprocates through the face width of the gear blank. The gear blank also moves relatively. The relative motion of the gear blank and the rack cutter is in such a way that they mesh and roll together as rack and pinion. The block indexing adjusts the job for generating the next set of teeth. The correct relative motion between the cutter and the job is given by a set of suitable gear trains. It also carries out the block indexing. As the blank and tool move along the respective paths, the cutter removes a small amount of metal each time, causing a series of facets that produces the involute curve form. This method results in production of teeth accurate to any size using only one cutter for a given module. Gear shaping can also be carried out by using a pinion cutter. The pinion cutter reciprocates and also revolves in a specific relative motion with the blank. This shaping action generates the involute tooth form, cutting the tooth edges facet by facet. Another process of spur gear generation is by gear hobbing, which produces gears with greater accuracy and higher flexibility. A hob is a set of rack cutters around a shaft. While the hob revolves, the work is also made to revolve at its corresponding relative speed. As the cut progresses, the hob moves parallel to the axis of the gear along with the face width, removing metal by progressive cuts. A hob also cuts all gears having the same tooth form and module regardless of the number of teeth. The hob is sharpened periodically in order to maintain high precision of the cut. Internal gears are produced for mass production by gear shaping using the pinion cutter. In case of large-scale production of internal gears in minimum time, broaching is preferred. A separate broach is required for every gear of different specifications. Spur gear teeth are subjected to finishing operations in specific cases where high accuracy is required, especially after the gears are hardened. Grinding process produces higher quality gear finish by removing tiny flats on the surface. The other common finishing process is lapping. It involves simply running the mating gears together with abrasive paste. It improves the surface finish by removing the scales. Gear shaving is a high finishing process in lesser time. The serrated edges of the finished tool shaves off the tiny flats on the surface. The product gear is inspected at various stages of manufacture. Individual elements such as run out, tooth thickness, depth, pitch, and involute profile of tooth are inspected after the completion of the gears. Thus, unlike in milling, the production of gears by broaching, shaping, and hobbing gives accurate tooth form, eliminating approximation of shape and size in minimum time.